Bismillahirrahmanirrahim. Assalamu alaikum dear students. How are you? Hope you're all fine. Today I'm going to deliver next lecture. This is chapter 13, Electromagnetism. In the previous lecture, dear students, we introduced electromagnetism, magnetic field, and force on a current carrying conductor. We derived the formula of that magnetic force. After listening to this lecture, girls, you would be able to understand magnetic flux and Ampere's law. Let me start with magnetic flux. Dear students, you are all familiar with flux. That was electric flux, and we discussed in electrostatics. How we define electric flux? Yes, the number of electric lines of force passing per unit area. Just in the same way, we define magnetic flux as the total number of magnetic lines of induction passing through any surface placed in a magnetic field. So, let me consider these magnetic lines of force producing magnetic induction B, and we just place a surface, and through the surface the lines of force are penetrating, these are passing. So what happens when we just rotate it? There is no change in the number of lines, that's why flux does not change. But by changing the area, the number of lines of force, they are affected. Similarly, when we rotate it through some angle theta, so what happens? This effect on the number of lines passing through it. Similarly, when the surface area is rotated through 180 degrees, then what happens? The flux, it becomes negative. Why? Because theta is equal to 180 degrees. Similarly, what happens when we just divide the total surface into number of small patches, each of it having area dA, then how we define the total flux? The total flux phi is equal to integral of B dot dA, where what is B? B is the magnetic induction. What is dA? dA is the area of small patches of the whole surface. All right. Magnetic flux is also defined as the dot product of magnetic induction B and vector area delta A. So B dot delta A is giving you magnetic flux. Abbreviation: magnetic flux is denoted by a symbol, that is phi, and it is given as delta phi is equal to B dot delta A. It means magnetic flux is an example of a scalar product, because delta phi is a scalar quantity which comes when we take the dot product of two vector quantities, that is magnetic induction, this is a vector quantity, and the vector area, that is delta A, because delta A is the vector which is always perpendicular to the surface. Alright, that's why it has a direction. That's why we call this area as area vector. So this is giving you the symbolic way to define magnetic flux, that is delta phi, and mathematically it is given by delta phi is equal to B dot delta A. So in the given figure, what we have, the lines of force are denoted by these arrowheads, that is B, and this A is the area vector which is always perpendicular to the surface. Alright, in that case, we open it B dot delta A according to the definition of dot product. What comes? B delta A cos of theta, where what is theta? Theta is the angle between area vector A and magnetic induction. So Delta phi represents the magnetic field lines passing through the vector area element delta A placed perpendicular to the field, which is placed perpendicular to the field. Direction of the vector area element delta A is normal to the surface area. The total flux through surface area A is given as. How to find the total flux? For this purpose, we introduce here sigma, as sigma is the sign of summation. So it means the total flux through the surface when we divide the total surface into number of small patches, and then we calculate B dot delta A for each surface, and then in the end we add all the fluxes for first surface, second, third, fourth up to so on. So we add all of them, then this gives you sigma B dot delta A, which is equal to B dot A. So that gives you BA cos of theta, where what is theta? Theta is the angle between B and A, between magnetic induction and area vector A. So as previously we noticed that phi is equal to BA cos of theta. So what are the factors on which magnetic flux depends? It depends upon three factors. Which one? B, that is magnetic induction, greater the number of lines of force, so more would be the lines passing through the surface, that increases flux. Secondly, it depends upon area. Greater the area of the surface, so more lines of force would be penetrating or passing through the surface. And the third factor is theta, where theta is the angle between B and A. What are the conditions when flux is maximum? If the surface is placed perpendicular to the field, let we consider this surface, how it is placed in a magnetic field perpendicularly. So what is the theta between A and B? Because this is the direction of area vector, which is along the direction of B. So what would be angle between B and A? That is given by 0 degrees. So we put theta as 0 degrees, so cos of 0 is 1. So in that case, flux, that is magnetic flux, is maximum, which is given by B into A. What are the conditions when magnetic flux is minimum? When we place the surface area in such a way that this area vector is perpendicular to the magnetic field. So in that case, what is the direction, what is the angle theta between A and B? It is 90 degrees, all right. And what is cos of 90? When we put it here in the formula, phi is equal to BA cos of theta, that is phi is equal to BA cos of 90. As we all know, cos of 90 is 0. So 0 multiplied by BA gives you 0. So flux would be equal to 0. That is the case when flux is minimum. Now, if we tilt the surface through any angle which lies in between 0 degrees and 90 degrees, so it may be 30 degrees, 40 degrees, 45 degrees, whatsoever. So that lies the flux, the value of the flux lies in between the maximum, that is 0 degrees, and minimum, that is 90 degrees. Now we come to unit of magnetic flux. The unit of magnetic flux is Weber. Symbol is W, capital W and small b. 1 Weber is given as, what is 1 Weber? 1 Weber is equal to 1 Newton into meter over Ampere. So, magnetic flux density. Magnetic flux density, that is B. So from the formula, what comes? We eliminate for B. B is equal to phi over A. Alright? Therefore, magnetic induction B can be defined as magnetic flux per unit area, also called magnetic flux density. So this B, that is equal to magnetic flux per unit area, is known as magnetic flux density. So what would be unit of magnetic flux density? Dear students, put the unit as I told you earlier. What is the unit of phi? That is magnetic flux, Weber. So Weber, and what is the unit of area? Meter square. So Weber over meter square is giving you the unit of magnetic flux density. So in that case, we are having a relation. In the previous lecture, I told you about Tesla. Alright, so 1 Tesla is also equal to 1 Weber over meter square. So we are having two units of Tesla. So the first unit I told you in the previous lecture, that was Newton over Newton over ampere into meter, and this is giving you the second way to define Tesla. That Tesla is also equal to 1 Weber over meter square. Now we come to Ampere's law. In order to understand Ampere's law, let me start the discovery. It was discovered by a physicist, Andrew Mary Ampere, in 1826. It relates the integrated magnetic field in a loop around a current carrying wire to the current passing through the wire. So, in case of Ampere's law, we calculate mathematically the value of magnetic induction which is produced because of a current carrying wire. So, as I told you in the previous lecture, that Ampere's circuital law, a current carrying wire carries magnetic field in a region all around it. So this law gives you a mathematical relation to calculate the magnetic field around a closed loop and the total amount of an element. So it was discovered by Hans Christian Ørsted. When an electrical current flows through a wire, it will generate a magnetic field. Where? Around the wire. All right. The presence of a magnetic field could be checked by placing a magnetic compass. Magnetic compass deflects, it means magnetic lines of force are present. And how they are present, and Andrew Mary Ampere calculated the magnitude of magnetic induction by a mathematical relation. Magnetic field induction over the closed loop is equal to mu naught, the total amount of current, and closed by the closed loop or circle. This closed loop or circle. For this purpose, let me consider a straight wire. That is a current carrying wire of magnitude small I. All right, according to Ørsted, is discovered in 1820. The direction of I is taken along z-axis. Let me consider here a loop of magnetic lines of force of radius r. R is the radius, and we place here at point A a magnetic compass just to check the presence of magnetic field. Yes, it deflects, shows the magnetic field. Now what happens? We bring it at some point B on the circular path through which we move from A to B, and we cover some distance dl. And this distance is also equal to AB, that is equal to length of the circular arc. So we perform work done dW, which is equal to B dot dl. So we just move the magnetic compass on different points on the circular path. So integral along the closed path is equal to B dot dl, which is equal to mu naught into I. where what is I? I is the current which is passing through the Y, and what is mu naught? It's the permeability of free space. So, the direction of the current could be calculated by right hand rule. Curl the finger, grabs it in your hand, stretch the thumb, indicates the direction of the electric current, and the direction of magnetic induction will be in the direction of the curled fingers. All right. Ampere's circuital law states that the dot product of B and delta L around an enclosed path is equal to mu naught times the total current enclosed by the path, that is B dot delta L. Here we have introduced a sign of summation sigma. Sigma, why? Because if you remember in the previous activity I told you, when we consider the circular path and we consider different points on the circular path, then we calculate B dot delta L for each point on the circular path, and then in the end we add all B dot delta L. Then what we get? We get the total work done, which is given by sigma B dot delta L, which is equal to mu naught into I, where what is I? I is the current. And what is delta L? Delta L is the distance, that is equal to length of the arc of the circular path. Let us consider a closed path. This is the closed path, and which shows the magnetic lines of force. All right, this shows the direction of current, and here is the presence of magnetic lines of force. Let us consider closed path around the Y in the form of a circle having the Y at the center. All right, it causes magnetic field around it. To calculate the magnitude of magnetic field B at a distance r from the conductor, Ampere performed a series of experiments and showed that magnitude of magnetic field is directly proportional to the current I. So, the greater the strength of electric current, then more would be the strength of magnetic field. It means more would be the magnetic lines of force. So, what does it mean? It means B is directly proportional to I. And it is inversely proportional to the radial distance from the conductor. So definitely as we move away from the Y, then what happens? This R, it changes, it increases, and when we are moving away it from the Y, then it means R increases, and by increasing R, definitely the strength of the magnetic field reduces. So it means what type of relationship exists between R and B? Inverse relationship. All right, mathematically we write down relation 1, that is statement that B is directly proportional to I and B is inversely proportional to R. When we combine 1 and 2, what comes? B is directly proportional to I over R. So definitely this one is not an equation. In order to convert it into an equation, what we do? Yes, we add a constant of proportionality, which is given by K. Let it be equation number 3. Alright, and this equation, in this equation where K is a constant of proportionality, and it is equal to mu naught over 2 pi, where what is mu naught? When we that is permeability of free space, pi, that is for the circular path we take pi. So when we put this value of K in equation number 2, what comes? We get this equation, that is B is equal to mu naught I over 2 pi r. After putting the value in equation number 3 and after making some adjustments, we get here equation number 4. Where in this equation number 4, this mu naught, which is a constant, it is known as permeability of free space, and it is defined as the ability of a substance to allow another substance to pass through it, and its value is given as. So you can find the value of mu naught. This question may come in your exams, that find the unit, derive the unit of mu naught. For this purpose, you will use equation number 4, and from equation number 4, eliminate for mu naught. Mu naught would be equal to B over I into 2 pi r, and when we put the values over here, that is the unit of I, unit of r, and unit of b over here, what comes? Mu naught is equal to, it gives you a numerical value, that is 4 pi into 10 raised to the power minus 7 Weber per ampere per meter. You can solve it. Equation 4 can be written as another way to write down the law, that is B into 2 pi r is equal to mu naught into I. Students, you can see here 2 pi r. What is this 2 pi r? Yes, this is giving you the circumference of the circle. When we start from A point and coming back to A point, what would be length of the arc, which is given by 2 pi r? As 2 pi r is the length of the closed circular path around the path, then above equation becomes B dot L is equal to mu naught I. So instead of writing 2 pi r, we write down L, because this much distance is moved along the circular path, that is given by 2 pi r and indicated by L. Alright, for any path element delta L we can write. So if we divide, if we consider different points on the circular path, then we come to path element, and for any path element, instead of L we write down delta L, that is P dot delta L is equal to mu naught I. So these are equation 4, 5, 6 different ways to write down Ampere's circuital law. If the path is exact circular, delta L is parallel to B. Then B dot delta L is equal to B delta L cos of theta, that is equal to mu naught into I. So these are all analogous equation. As theta is equal to 0, what does it mean? B and delta L having the same direction. Then what happens? Cos of 0 is 1. So what we get? B delta L is equal to mu naught into I. Summing over the entire closed path, sigma B dot delta L is equal to mu naught I, which is Ampere's law. The closed path is called Amperian path. Always remember, the closed path where we apply Ampere's law is known as Amperian path. This law can be applied to any closed path around a uniform magnetic field. Thank you, dear students.